Good afternoon. Sorry. Good afternoon, good evening, everyone. Welcome. My name is Francisco Daí. I'm Associate Professor at Federal University of São Carlos, and I am pleased to introduce Professor Denis Bonheure from University of Bruxelles. Professor Bonheure has been an expert in mathematical analysis, especially on PDEs and calculus of variations, with many outstanding contributions in elliptic equations. He is going to talk about equilibrium configuration of a rectangular obstacle immersed in a channel flow. Welcome, Professor Bonheure.
Muito bom dia. Funciona o som?
Ok.
Você está ouvindo?
Estou perfeitamente, professor.
Ok, tudo bem. Desculpe pelo atraso, que você está... ok, em inglês, não é?
No problem.
Ok, well...
Thank you for accepting the invitation to be in our seminar, and now the word is yours. Thank you.
Okay, so you see my screen? Fine?
Yes.
Okay, so for those who are not in San Carlos like me, I put a picture, well, it's almost night here in Belgium. So I'm very happy to be remotely in San Carlos. I would prefer to be there. I think the only advantage to be in a remote way is I won a 10-hour flight, but I think it's the only advantage. And I would have preferred to be on site, of course. Okay, so the work I'm going to present, I'm sorry, I changed my title in the last moment because I realized that I wanted to talk about something a little bit too dynamical for this conference, which seems to be more elliptical. So I decided to talk about something related to Navier-Stokes equation. And this is a joint work with Paolo Galdi from Pittsburgh University and Filippo Gazzola from Milan Politecnico. Okay, so let me go on with a motivation. So as you know, in the oscillation of bridges is an important issue in engineering. And when you have a wind attacking a bridge on the, let's say, transversal direction, then the bridge starts to oscillate up and down. Okay, and my talk is in a way a contribution to try to understand this kind of behavior. Well, we will be quite far because this is a model of a bridge. So towers, I won't discuss anything about towers. Main cables, so these things, I won't discuss anything about main cables. Angers, I will not assume there are angers. In fact, I'm only going to consider like this part, the span, like a plate. Okay. And at the end, you will see that, in fact, I'm going to consider only a cross-section, in fact. So I will just discuss a 2D model where you see that you want to model the movement of a cross-section of a plate. Okay? So that's it. Here you see that you have a wind coming from the right, attacking a plate, transversal wind. You have the plate, and then here you see vortices. And these vortices create the up and down motion of your plate. And this is called, in fact, vortex shading phenomenon. And let me show you a picture, in fact, a video. I hope the video you can see. Well, I can see it on my iPad, but I see the streaming quality is quite bad. So you see that there is a flux entering from the right, and your cylinder is going up and down. Of course, your cylinder cannot move in that in the direction here, otherwise the cylinder will be pushed in that direction. So the cylinder is only able to move up and down, and you see that a transversal flow here, a transversal flow here creates this vortex shading phenomenon. Okay. Now, let me discuss a little bit about what are the implications of this lift and how this lift appears. So this picture is in fact a picture of two stationary solutions of the Navier-Stokes equation. You have a flow coming here, an inflow, let's say, and then you see that these are the this is the solution, and here your solution is symmetric. Okay, so you have symmetry of your solution here, and the same here. And so, of course, if you have symmetry, then there is no force, there is no lift. No force is acting on this vertical direction. Okay. So if you want to have lift, if you want to have a motion in that direction, you need your solution to be, in fact, non-symmetric. So this is a case where you have lift. And so if you have non-zero lift, you see that you have your symmetry line here. Okay. And of course, I'm sorry, there is a delay between what I write on the iPad and what I see on the screen. I don't see anything on the screen now. So this is frozen. Okay, so you see on the screen okay, so now you see on the screen. Okay, so you see that if you flip the solution in this way, then you have another solution of your equation. So in fact, when there is no lift, there is non-uniqueness of Navier-Stokes. Okay. And this means that this is kind of a difficult issue, because you are in a regime where you don't have uniqueness of solution for Navier-Stokes equation. Okay. Now there is also something very interesting. In fact, I would like to go back to my motivation here when you had the bridge going up and down. So you have your bridge going up and down. And one can ask what mathematical mechanism can be behind this. And in fact, probably, I say probably because there are no proof for the moment, but probably the mechanism which is behind is this one. And I hope you can see. So this is a flow coming from here. So this shows you that when you have an inflow, and this is an obstacle, you see that the inflow, well, the flow past an obstacle seems to tend to a steady position, and you see that this steady position seems to be symmetric. Okay, but now you see that there is something here and something here which is not symmetric. And in fact, this is the so-called von Karman vortex street. And you see that there is now, in fact, you have bifurcation from steady state to periodic motion. Okay. And this is what we call in bifurcation theory, this is called Hopf bifurcation. Okay, now for this here, let's say a liquid past the cylinder or a flow past the cylinder, you can look at, there is an ARMA paper by Paolo Galdi, where there is the functional setting. Okay, the fact that there is indeed bifurcation is not known theoretically because you have some spectrum of some operator to study, and this spectrum can be understood only numerically. Okay, so here is okay. Okay, so here is about the modeling of the problem. I'm sorry, but there are so many troubles of, okay. About the modeling of the problem, there are some, at least 3 levels. 3 levels. I don't know why this is not coming anymore. Okay. You see now? Okay. So there are 3 levels of modeling. The first one is about the structure. In this case, you usually end up with a hyperbolic equation. Of the type, let's say, UTT plus biharmonic of U, blah, 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 blah. And in fact, you have to assume how the aerodynamics appear in the model. Okay. Then you can say, okay, so in this case, you really want to understand the structure. So you have the equation for the structure, and you assume how the aerodynamic force appear in the model. So I mean, you assume somehow how the flow is acting on the structure, on the bridge, for instance, on the plate. And then you can say, okay, now I want to study the fluid. Okay. And if you want to study the fluid, then of course, what you study is the Navier-Stokes equation. And you have somehow to say that you prescribe or you fixed, either you fixed or you prescribe the motion of the obstacle. So Navier-Stokes in, let's say, RD or channel or whatever, minus omega, and omega is the obstacle. Okay. And somehow you have to fix, either you fixed, so this omega can be omega of t, so it's either fixed or the motion of omega depends on t. And then you have the third level of modeling, which is by far the hardest, because you want to couple the fluid to the structure. Okay, so you want to take into account the mutual interaction which takes place at the interface where the fluid meets the structure. Okay, so in terms of mathematics, structure is hyperbolic, fluid is parabolic. So you have a hyperbolic parabolic coupling. Okay, and that's it. That's the level I want to discuss a little bit today. let me advertise a little bit. I'm sorry that I cannot see any of your face, so maybe someone can tell me in the chat if you recognize this guy here. His name has been mentioned many times during the conference. So I don't know if Gustavo can recognize this guy. No, nobody. It's very strange. Odair, you know who is this guy?
I don't know, Stokes? Navia?
Sorry?
Stokes? Navia?
No. In fact, his name was mentioned. His name was mentioned in Augustus talk.
Okay.
So in fact, his name is Vladimir Mazia.
Okay.
That's not a joke. It's really a picture of him. This telephone is killing me. Shit. Okay. So in fact, if you want to have a survey of what I discussed, this level of modeling and so on, you can look at this paper here, which is written with Gazzola and Sperone, and it appeared in Rendiconte di Linceo. About the second level of modeling, I mean where you want to study the structure. So this is about structure. So for the structure, there is this paper with my friend Ederson, who is certainly listening, from USP San Carlos, well, São Paulo, but at São Carlos. Where we assume that we look to periodic solution of the structure when we put a periodic forcing. Okay, and then there is another paper, which is the one I wanted to present, but I decided to change my mind, which is with Gazzola, with Lazieka and Webster, and this is about when you have piston theory. Okay. So with all these technical issues, I will be short on time, but let me explain a little bit what I want to study. So the bridge or the plate is like that. Okay. But if I want to study this big model, this 3D model with a flow coming here, so this would be the wind. This is hard because then you have to use 3D Navier-Stokes. And 3D Navier-Stokes is a big deal, so seems not to be easy to look at this. So in fact, the easiest thing to do is just you take this K, which is a cross section of my bridge, of my plate. And so I take a cross section and I make it 2D. Okay. So this is a cross section. And then, of course, I have my wind coming here. Okay. Now, the motion of the plate can be up and down. Do you see me? Yeah. Do you see my slides or not?
Yeah, we are seeing your slide, but you can hear you also now. But your image is freezing.
My image or my slides?
No, I'm not sure if the slide is freezing also, but your image for sure. But if you change the slide a little bit, I can check it.
I can.
Now, okay, the slide change.
Okay. I don't know about the
slide seems to be okay.
Okay, I don't know about.
But okay, then it's going well.
Okay, so let me go on.
Okay, thank you. Sorry about the interruption.
Okay, so the bridge can go up and down, and it can also rotate around the fixed pin. Okay. Okay, so the thing I want to discuss today is about this motion, so up and down of the bridge or the plate, and the rotation around the fixed pin, assuming that you have a flow in a fixed channel. So this is a channel. You have an inflow, which is this is a parabolic inflow, quasi type. Okay, and then you assume that at infinity you return to your quasi. Okay, 10 to quasi plus infinity, and we have to discuss the problem in two steps. So when the motion is up and down, or where you have the rotation, things change. And for the moment, we are not studying the problem with 2 degrees of freedom. So only 1 degree of freedom. Okay. The 2 degree of freedom is a work in progress. Okay. Okay, so let me discuss what is it about. So the equation for the fluid is the Navier-Stokes equation. Okay. This is a fluid structure interaction problem. So you have to look at the boundary. So let me go back. The thing is that you have to look at what happens where the structure is touching the fluid. This is a solid, so we don't assume that this can be deformed at all. So this is a solid. So this will mean that we will have a EDO for the center of mass. Okay. Okay. So at the place where the fluid meets the solid, you have to impose a dynamical condition, which is that on the boundary of the solid, there is a matching between the velocity of the obstacle, which is h point, and the velocity of the flow, which is u. Okay. So this condition at infinity here is the Poiseuille. And now you see that, of course, your body is moving like with a pendulum equation, oscillator, with a force coming from the fluid. Okay.
Denis, we are not able to hear you anymore.
Você não ouve?
Agora sim, yes.
Eu não sei o que aconteceu. Eu não mexi nada. Mas você está ouvindo? Tá funcionando?
Tá. It's okay. Sorry about the Portuguese for the guys that can't understand. Sorry. Denis, yeah, it's okay.
I can continue?
Yes, please.
Okay. Okay, so in this equation, of course, I have to recall you that this object here, divergence of the Cauchy stress tensor, of course, the Cauchy tensor is 2 times the symmetric part of the gradient minus the pressure. So as you may be more familiar with, this gives you the gradient of the pressure minus the Laplacian of u. Of course, u is a vector. Okay. Now let me tell you more about that. What we assume, we want to, in fact, show, and this is, it seems to be ridiculous, but it's hard to prove mathematically. We want to show that when let's say, we should call this like a Reynolds number, or viscosity number. When this Reynolds number is small, so when you are close to the Stokes equation, you want to show that the unique equilibrium position of the obstacle in the channel is the middle position. Okay. Now, in fact, this Reynolds number is kind of, let's say, it's scaled like reference velocity divided by the viscosity. Well, the viscosity, yes, and it's also related to the let's say magnitude of the Poiseuille flow, of the inflow. Okay, maybe I'm not discussing too much on this. We assume a strong force condition on this F. So this F here, we suppose that it satisfies this condition here, which means that the repelling force becomes infinite when the obstacle is close to the wall of the channel. Okay. So you want to prove equilibrium. So equilibrium position means ut equals 0, h dot equals 0. And so you end up with a steady Navier-Stokes. And this is the, let's say, fluid structure condition. Okay. So you want to prove that there is only one position, and in fact, when the body is in the middle of the channel, that solves this problem. Of course, for each h, this has a solution. For every h, look that the domain, the fluid domain omega depends on h, but one and only one satisfies this condition. Okay, that's what you want to prove. Okay, now if you look at the case where the body is moving around a fixed pin, then of course your body is moving according to a rotation of angle theta. And now your fluid domain is an omega theta. And so the problem to solve, now you have what is called a torque. This is a torque on the body. Okay. And you again have a restoring force, a G. And for physical reason, it's natural to assume that the G is odd, because going up or down, I mean, I cannot show you with my hand because you don't see me. But okay. And the thing is that for physical reason also, you assume that going to the position pi over 2 is not possible, so you put a strong force condition. Okay? So now the fluid structure condition is this one. You have that the repelling force has to match with the force coming from the body. And this is Navier-Stokes again. Okay. Okay. So this is the result. Alors, so the theorem is the following. We can show that assuming F is C1, G is C1, there exists a universal rho R0 and a universal lambda 0, which do not depend on F and G, such that if the R is smaller than R0 and lambda is smaller than lambda 0, then both problems have a unique solution. Which is in fact the middle solution. Middle solution. Angle 0 solution. Okay. Now to prove this is a little bit of computation, and I cannot show you everything, but the first thing to do, is the existence of Navier-Stokes for each h or theta. Okay, and this is okay. This you can prove, and you have to assume that R times lambda are below a certain constant depending on L, and this is not a technical issue. Sorry about that. This is a true open problem posed by Libre. So if R is big or lambda is big, we don't know if there is a solution. This is totally open since Libre. So it's really a, and the most outstanding people in Navier-Stokes equation, they were not able to solve this. Okay, and then you have these a priori bounds which are universal and will be important for what I'm going to discuss. Now, to explain a little bit about proofs, I have to distinguish between the up and down case and the rotating case. Now, the idea, because I will be short on time and I don't want to take your time, the idea is the following. You define an auxiliary Stokes flow, and this Stokes flow is encoding somehow the condition on the obstacle. And you see that since the Stokes flow is constant on the obstacle and 0 on the boundary of the channel, of course, you have a boundary layer when the obstacle is close to the boundary of the channel. And so you have only bounds which depends on 1 over epsilon to the 3 over 2. Okay, so there is an explosion close to the wall. Okay. Now, let me show you this lemma. In fact, this lemma is very important because it shows you that this is the force of the fluid on the solid. And you see that this is computed with on a surface integral. And in this T here, there is a pressure. And the pressure is kind of difficult to estimate. And as I will need to prove differentiability of this guy, a surface integral is also a big difficulty if I want to prove differentiability with respect to the shape. So in fact, what we prove here, we prove that this can be transformed into a solid integral. And you see here, this is solution U of the Navier-Stokes, and this is the auxiliary Stokes flow. So no explicit pressure. Okay. Now, how you do that? This is a very simple. You multiply the Stokes equation by the solution of the Navier-Stokes. You multiply the equation of Navier-Stokes by the solution of the Stokes. And then you show that, in fact, you have this quantity which is 0. And this shows you that these guys here is equal to this guy here. Okay. Okay. This was to explain things. Now, to prove uniqueness, we define a function which is, you want to prove that you have a unique solution such that this here is 0. So unique equilibrium means 1 and only 1, 0 of psi for small Reynolds number. Okay. And so the idea is to use an implicit function theorem. And to prove an implicit function theorem, you need regularity. And so you need to prove at least that this function is C1. And you see that in this function, you have a shape. You have an S here in the solid integral, and S depends on H. So you have your channel here. You have your body here. And the position here. This is H of the center of mass. Okay. So you have to prove that this quantity is smooth with respect to H. Okay. So you have to do a shape derivative. And this goes back to François Murat. And I forgot his surname, Simon. I don't remember his. And Simon. Okay. To prove that indeed you can compute, you can prove that in fact the solution depends smoothly on the position of the body. Okay. So remember that this channel is omega h is the channel minus this body, and this body is moving. Okay. Okay. So now, by symmetry of the problem, when you have so this means when h is 0, the middle solution satisfies psi equals 0. This is by symmetry. Okay, because you are integrating on a symmetrical object, a symmetrical solution, a symmetric solution. And for the same reason, you can show that this Stokes problem here, enjoy this symmetry here. Okay. Okay. Now, with the lemma about changing the surface integral into a solid integral, this psi is now defined as this quantity here. And somehow you have to show that the restoring force F is the winning term. Okay. This is Stokes, Navier-Stokes, and this is Stokes auxiliary function. Okay. Now look that here I said that when you have Stokes, this Reynolds number here is 0. So there is no lift. And I don't know if you had some lectures on fluid dynamics. This is related to the d'Alembert paradox. Okay. So in fact, Stokes is not a good equation to account for lift and drag. You don't have drag also for Stokes. You can only see drag with Navier-Stokes. Okay, so now let me show you how you prove that indeed this psi, this function psi, has a sign, the good sign, which is strictly positive when the Reynolds, when the R is positive, and strictly negative on the other side. In fact, you first use so you have three cases. The first one is your body is close to 0. So when h is small, and then you use the implicit function theorem because you can compute the derivative of your function psi with respect to h. These include the shape derivative of the solid integral. And by the implicit function theorem, you know that you have a unique 0 close to 0. Okay. Now, a second case is when h is close to the boundary. So this means that the body is close to the boundary. And then you have to invoke, and I will not discuss the strong force. And then you have the intermediate h, and this is just compactness. In fact. Okay, so I'm short on time. I see that you want me to finish at 2. Well, you want to finish now. So this is the case where you have rotation. And in fact, you have exactly the same kind of result. Just look at the condition for the auxiliary Stokes solution, and you can express now the solid integral. The torque on the body is expressed with a solid integral again with this W here, which is this function here. Okay, that's it. Thanks a lot. I'm sorry for all the troubles.
Thank you, Denis. We apologize for the problems for you and also for the audience. But it was a very nice talk. Thank you so much for being with us, and we are very grateful for you have accepted the invitation. We cannot see you yet, but let me see if we have some questions. There are some comments. I think that Gustav will put the comments in the YouTube, but there is no question here. But I don't have a question also. But I want to hear about because in the beginning of your talk, you explained the connections with people from engineering and other kind of science, applied science. So I want to hear you about what kind of interaction with other scientists of the other areas do you have in this program?
Well, somehow you don't really interact with people in engineering or physics because they know everything already. Everything they know, you want to prove it mathematically, and that's very tough. So fluid dynamics is a very strange world where you have numerical computation that you cannot explain and you cannot prove, and you see phenomena for which you have paradoxes, And so in fact we try to understand mathematically some questions for which, I mean, for this kind of Hopf bifurcation, if you talk to an engineer, he will say that it is clear that it's a Hopf bifurcation. But to prove it mathematically and with a rigorous theorem is very hard.
Thank you, Denis, again. I think that now I am freezing. Okay, I'm back. Thank you again, Denis. And okay, you are not have proved all the things, but the word is working, more or less. But
Yeah.
we are here. Thank you, Denis.
Bye-bye.
And bye-bye. Thank you very much.
Bye.
Let me see if you have more. Okay. Now we have a small break, just a few minutes. I want to invite you to continue with us for the next talk that will be in, I don't know, maybe 5 minutes. Thank you so much. Bye.
Boa tarde a todos. Meu nome é Olímpio Hiroshi Miyagaki, sou do Departamento de Matemática da Federal de São Carlos. Obrigado por estar presente ao nosso evento. Good afternoon and welcome everyone. My name is Olímpio Hiroshi Miyagaki from Math Department, Federal University of São Carlos. Thank you for joining us in this afternoon talk. We're going to resume this conference in this last session. It is an honor for me to introduce Professor Giovany Figueiredo. He will talk about positive, maximal, and minimal solution for non-homogeneous elliptic depending on the gradient. Professor Figueiredo, he has many outstanding papers about the existence, multiplicity, and the non-existence results for Kirchhoff problem, critical exponent problem, singular problem, fractional problems. Among them, I would like to mention outstanding paper with Claudio Oliveira Alves about Shokar equation. Welcome, Professor.
Thank you so much, Olímpio, for this very, very nice introduction. Can you hear me?
Yes. Clearly.
Do you have? Can you see my screen?
Yes. Now it's.
And now?
Now, better.
Okay. So, firstly, I would like to thank the organizing committee for the opportunity to talk about this work that was made with my friend and brother Gustavo Madeira from Universidade Federal de São Carlos. In this talk, my friends, I would like to show existence of positive, maximal, and minimal solutions for a non-homogeneous elliptic equation, where the non-linearity depends of the gradients of the solution. Let's get started. I have with a long but necessary previous result. There are several existence results for this class of problems where the non-linearity depends on the gradient of the solution. For example, in the papers below, we will consider Laplace operator and the super solution method. In the first paper, Abdelawi, Dallagro, and Peral show existence of solution with critical grounds in the gradient. In these two articles, do two Alves, Claudio Alves, Moa Soaí, and Davi Arcoia, Bocardo, Leonor, and Porreta, they also show existence of solution for a problem that appear the gradient of the solution in a singular term. In this another paper, Mabel Cuesta Leon show existence of maximal and minimal solution, and she uses a very nice argument that involves Zorn lemma. Gaslink, Papagiorgio show existence of solution for a problem with dependence on the gradient using fixed point argument. This one is a very, very nice paper do de Jairo Figueiredo, Girard Matzel. They freeze the gradient term. After that, they use the rational method, more precisely Monte-Pass theorem, in order to recover the solution of the original problem. They use a iterative argument. So, here I have a paper do Claudio Alves, Carrião, and Luiz Faria. They use the Galerk method to show existence of solution. Luiz Farias again, Olympe Miyagaki, Montreanu, they show existence of positive solution for a problem with the very, very new PQ Laplace operator. Again, Jairo Figueiredo, Jean-Pierre Gosses, Humberto Chiori, Pedro Bila, they study a problem with P Laplace operator and the gradient term in this equation with a natural grounds, and they use a change of variable. After that, they apply variational method. Here, the paper due to Hamilton Bueno, Grey Hercules, Umpano, Ferreira, they study a problem with P Laplace tool. In this paper, Claudio Alves, Carlos Alberto Santos, and Joe show existence of solution with the presence of a gradient term E or N. And in this problem appear suitable weights in order to overcome lack of compactness. Costa Fernandez show multiplicity for a problem with P Laplace operator and with a critical grounds in the gradients. Farati Montreanu Puglisi freeze the gradient 2 in this paper. After that, they use variational method in order to recover the solution for the original problem. They using a fixed point argument. Liu, Montreanu, Zeng study a problem with a singular term and the singular term in the presence of the gradient 2. Papa George, Radulesco, republished, study a problem with singular term and the gradient term 2. But in this case, they consider Neumann boundary condition. Bocardo, Murat, Puel, after that, Luiz Faria, Olympe Miyagaki, Montreanu consider in these papers Leray-Lyon's operator and dependence on the gradient. Other good papers appear with dependence on the gradient, like the papers due to Davi Arcoia, Carmona, Pedro Martinez Aparicio, Davi Ruiz, Antônio Soares, Marcos and Marcelo de Montenegro, and so on. Now, I'm talking about the main results. In this talk, you show an abstract result of sub-super solution method type for this non-homogeneous elliptic equation, where in the nonlinearity appear the dependence of the gradients. After that, you apply an abstract result in order to show existence of positive maximal and minimal solution for some class of non-homogeneous elliptic PDEs involving unbounded singular logistic source. In fact, I will show this an abstract result for 3 applications. Now, an important remark, such positive maximal and minimal solutions will be between not necessarily bounded sub-solution and super-solution. In some moment, I will define an auxiliary problem, and I need to define a functional associated to an auxiliary problem. So I need to put some hypothesis on the function A that appear operator, and in the first hypothesis, with the first hypothesis, I can prove that the functional associated to our auxiliary problem is coercive. In the second hypothesis, I can use the second hypothesis in order to show that this functional one is really weakly Lorentz semi-continuous. with the nest hypothesis, I can show a comparison principle for our problem. Finally, with the last hypothesis, I can show a regularity result for our problem. So these are the hypotheses on the function A that appear in our operator. In order to show the generality degree of our operator, I will give some examples about the function A. For example, in the first example, A equal 1, I'm talking about the classical Laplace operator. But the function A can be this way. In this case, I'm talking about the very new PQ Laplace operator. The function A can be this way. In this case, I have a strange but very nice operator, named P Laplace-like. Finally, the function A can be this way. In this case, I'm talking about the generalized P curvature operator. Of course, if P equal to, I have the classical mean curvature operator. Now, my friends, I would like to say some words about the first main result. The first main result is a non-uniform gradient estimate for an equation related to our problem. The first main result is like this. Consider this equation, this problem, with G in LS, with S grade N. So, there is a unique solution for this problem, and this unique solution satisfies this estimate. This estimate involves the L infinite norm of the gradient of U and the L infinite norm of the solution U. This one is the first main result. In the proof of the first main result, use arguments can be found in Seren's paper, Siank, and Mazia's paper. In order to enunciate the second main result, you define solution, sub-solution, and the super-solution for our problem. Here, I have the definition of solution for our problem, and here I have the definition of the sub-solution and the super-solution for our problem. With these definitions, I can enunciate the second main result. The second main result, if you consider a couple of sub and super-solution for our problem, if sub and super-solution are ordered, and if you have these grounds of the function f, where is in this interval, then you conclude there is a solution, at least a solution between the sub and the super solution. Moreover, there are the minimal and the maximal solution between the sub and the super solution. This one is the second main result. For the proof of second main result, my friends, use a combination of theory of pseudo-monotone operators and Zorn lemma. Moreover, you also some arguments can be found in Cuesta Leon, Dan Sui, Duell, and Peter Hesse. I would like to repeat the important remark that in this talk, sub and super solution need not be bounded. Okay, now I give a sketch of the proof of the first main result. To this, I consider dysfunctional associated to our linear problem. Use the grounds on the function A, below and above, and the hypothesis on the function G. You can conclude that the dysfunctional one is still in class. In the hypothesis 2, I have that the capital A is strictly convex. So, with this hypothesis, I conclude that dysfunctional one is weakly lower semi-continuous. Use the grounds of the function A below. I can conclude that dysfunctional one is cohesive. Now, I have that the dysfunctional one has a unique critical point, which is the unique solution of the linear problem. Now, I will prove the estimative involving the solution and the gradient of the solution of the linear problem. To this, I consider this function a tilde, and remember that I have that for hypothesis this function is increasing by hypothesis. So I can use theorem 4 and subsequent remark in Series paper and conclude that the right-hand side of this estimate above controls the L-infinite norm of the solution. So in this first step, I have this inequality. Now I use the grounds of the function A, and I get these grounds below and above for the function A tilde. And a direct computation, I get this equality. With this equality and the last hypothesis about the function A, I get this another inequality. Now, using this the inequality 5 and the inequality 6, these inequalities allow us to use estimate 7.1 in theorem 3.1 in Ciantes-Mazias paper to conclude that the right-hand side of that estimate controls now the L-infinite norm of the gradient of U. And in this case, the first main is the proof of the first main result is complete. Now, I would like to say some words about the proof of the second main result. The proof of the second main result is a consequence of several lemmas in this section. The first one is lemma 5. The lemma 5 says, if you have a sub-solution and a super-solution for all problems, there is a solution between them. In order to show this, I define another function G like this way. With this function G, and considering the hypothesis of the function F, I can show that this function is well-defined, bounded, and continuous. Now, I'll introduce an operator B. Operator B is this one, and in this operator B appears this function PC, such that I define PC here. The function PC is called the penalization function. So in the operator B, I have a penalization function PC, which is defined like this. So as a consequence of the grounds of the function A, you can conclude that B is well defined, continuous, and bounded. And considering a compacting bedding from W1Q0 into LQ, and the grounds of the function A2, you can prove that B is pseudo-monotony. Now, using the grounds of the function A again, and the definition of G and PC, you can prove that B is cohesive for tertalage. So, collecting the above information, I can use the very new Mint-Brown theorem, and can conclude that this problem has at least a solution. Now, using this special test function, I can prove that the solution of this problem is below from the super solution. Using another special test function, I can show that the solution of this problem is above from the sub solution. So the solution of this problem is between the sub and super solution. But by definition, if the solution of this problem is between the sub and the super solution, the penalization function PC is 0. So, in this case, the solution of this problem is a solution of our problem, of the original problem, and it is between the sub and the super solution, and the lemma 5, the proof of lemma 5 is complete. Now, I will show the existence of maximal and the minimal solution. For this, I will say some words about a lemma technical. A technical lemma, this lemma 6 is a technical lemma, and it says, if you have a couple of super solutions, and if you consider the minimum between them, this minimum is a super solution 2. If you have a couple of sub-solutions, the maximum between them is a sub-solution 2. Since the proof of this lemma is technical, allow me not show the proof here, please. Okay? I define in this set. In this set, I can use I will use the Zorn lemma in order to prove the existence of maximal solution and the minimal solution. In this set are the solution of our problem between the sub and sub solution. So this set is not empty, of course. Okay? In the second result, this set is compacted. This proof is very easy because here I use the compacting bed from WQ0 of omega into LQ of omega. Now I prove that this set is directed. I take 2 points in this set. Not that these points are in solution between the sub and sub solution, but if you take the maximum between them, this function is a sub-solution for our problem. So, I see this another set, here sub-solution, here super-solution, but I say that if you have sub and super solution, I have a solution between them. With these arguments, I can conclude that this set is upward directed. With similar arguments, I can prove that this set is downward directed, and In this case, I conclude that this set is direct. So, the second crime, everything has an upper bound. I use corollary 7 in a Lama Tarantellos paper in order to conclude that there exists a sequence in the team that D6 converges to supreme of the team. I remember that this set is compact, so this supreme is achieved, and if this supreme is achieved, the claim 2, the proof of the claim 2 is finished. Now, you are in position to apply Zor's lemma, which provides a maximal element U star in this set. I take this point in this set, and since this set is direct, I have these two inequalities, but with these two inequalities, I can conclude that there is a maximal point in this set. Is a consequence the fact that this set is direct, and everything has an upper bound. So, with a similar argument, I can prove that the existence of minimal solution for all problems between the sub and the super solution, and the second result is finished. A remark here, with minor changes, I can prove that the second result, and for or in this another interval. So, I would like to say some words about 3 applications, and you begin with a compilation of elliptic regularity, the strong maximum principle, and the comparison principle for this linear problem. The regularity result is this one. If U is a solution of this problem, then U has this regularity. Moreover, this solution satisfies this inequality. This solution satisfies this estimate. The second result is a strong maximum principle for this linear problem. Finally, I have a comparison principle for this linear problem. The regularity result follows by these 2 Lieberman's paper. The strong maximum principle follows by a paper due to Toxdorf, and the comparison principle follows from arguments that found in Gedda and Veron's paper. Now, finally, the first application. In the first application, I have the presence of the gradient with the potential R. I have a function f. The hypothesis on the function f is like this. F is greater than this positive number. F is in LS for S greater than this number. And with this hypothesis, I can prove the existence of sub and super solution for all problems. Then I can conclude that there is a maximal and minimal solution between them. Theorem 9, if R is less or equal Q minus 1, for lambda small, the first application has positive maximal and minimal solution. I start considering U underline be the unique solution of this problem. with direct boundary condition, of course. Using the maximum strong maximum principle, I can conclude that this unique solution is positive. Since, by hypothesis, f is greater than this number, and since this term is positive, I can conclude that the U underline is a sub-solution for our problem. Now, I will see the super solution. I consider U overline be the unique solution to this problem. Now, I'm using here the first main result. The first main result involves the L-infinite norm of the gradient of the solution of this problem. And it shows lambda like this one. I have that U overline is a super solution for our problem. Now, I use the comparison principle. Using the comparison principle, I can conclude that the sub-solution and the super solution are related. So, I can use here the abstract sub-solution type result in order to conclude that there is a positive maximal and minimal solution between the sub and the super solution for this first application. So, I have some words about the second application too. The second application is a logistical equation type where L is greater than Q minus 1, B is in L infinite of omega, and the war is less or equal Q minus 1, and if you consider lambda greater than this number, the second application has positive maximal and minimal solution for all with 3 non-negative small. This constant appear in the grounds of the function A that appeared in our operator. Okay? I define this functional one. This functional one is a functional associated an auxiliary problem. More precisely, I put 0 here, consider only this part, and define this functional associated to this auxiliary problem. Use the grounds of the function A and standard arguments. I can show that this functional is a weakly Laurent semi-continuous. You claim that this functional is cohesive, and here you give more details following Manuel Dalpinho's paper. The argument is by contradiction. Suppose that this functional is not cohesive. So I have a sequence with this divergence, but this energy is bounded above. I use in the definition of the function I, and I can conclude that this divergence is true in LQ of omega 2. Now, I define Vj like this way. So, use the grounds of the function A again. This functional satisfies this inequality. This inequality implies this another inequality. With this, the last inequality, I conclude that Vj is bounded in W1Q0 of omega. So, I have this convergence, and using this convergence in the last two inequalities, I have this inequality, but this inequality is a contradiction. So, I have that this functional is cohesive and it has a global minimizer U underline in WQ0. So, use a very new argument, I can conclude that this U underline is a solution of a problem, is a non-negative solution to this problem. So, use some arguments can be found in Tan e Fang's paper. I can conclude that U underline solution of this problem is in L infinity. Now, using the very nice paper due to Lieberman, I have that the U underline is in C1 beta. This has this regularity. Using the strong maximum principle, can be found by Patricia Pucci and Seri, I have that the solution of that problem is positive. U underline is positive. So, now, since the term gradient is positive, from a direct calculation, you can prove that U underline is a positive sub-solution for the second application. Now, I take a positive large constant as super solution. Of course, U overline, which is the constant, and the sub-solution are Doride. So, I have a positive and maximal, positive, maximal and minimal solution for the second application. Now, my friends, I have the last application. The last application, I consider the presence of the gradient in a singular term. And this singular term with the potential has a particularity. This potential is just positive, not be between 0 and 1, just positive. And the function m satisfies this hypothesis. This hypothesis allows consider just alpha positive, and this argument appeared the first time in this very nice paper do Itu Pereira and the Elvis Silva So I consider U underline be the unique solution of this problem. Now, I use the regularity result and the strong maximum principle of the linear problem and conclude that the unique solution of this problem has this regularity and it is positive. Now, I'm using here the first main result. The first main result involves the L infinite norm of the solution of the linear problem and this number. So, with this estimate, and it shows me like this way, I have that U underline is a sub-solution for the last application. Now, I use comparison principle. Use the comparison principle, I can conclude that this function is in L infinity. So, I will take the super solution as as U overline be the unique solution of this problem is the candidate a super solution for us. I use the regularity result in the strong maximum principle for the linear problem. I can conclude that U overline is positive and it has this regularity. Now, using for lambda large, I get this inequality, and with this inequality, I can use the comparison principle, and I conclude that the sub-solution and the U overline are ordered. Moreover, I can use this inequality, natural inequality, and I use the first my result again that involves the L-infinite norm of the gradient, and I can show this inequality. With this inequality, since I consider U less than Q minus 1, I conclude that U overline is a super solution for the last application. In this case, I have maximal, positive maximal and the minimal solution between them. I'm stopping here, and thank you very much, and congratulations for this very nice meeting.
Thank you, Professor Giovany, for nice talk with a wonderful subject. I will see if there's any question here. Let's see. I don't see any question, but just for curiosity, Giovany, if you change the boundary condition, not delicious, but put in Neumann condition, do you think it's working?
I think yes, Olympio, but it's necessary to make the calculation. But I feel that this result is true. But I think this is another paper, another publication.
Another for whole space, how do you think?
Sorry?
For RN.
The big difficulty in RN is the lack of compactness. I think if you put a suitable weights or another argument in order to overcome lack of compactness, I think that the result is true, but it's necessary to see a question about regularity, about strong maximum principle, about comparison principle. I think it is a very difficult problem when you change omega by Warren.
I think it's a very interesting result because your operator include mean curvature operator.
Yeah.
Very... Okay. I don't have any. Yes, we don't have any question. So, thank you very much again for accepting our invitation for delivering a wonderful lecture. Thank you very much, Professor.
Thank you, Olympia.
Okay. Now, I'm going to give you some warning to close this session. After my word, I give it to my colleague, but I want to say only thank you. I would like to say only thank you very much for all speakers for having accepted to deliver lectures. All those present at YouTube for attention. And we would like to thank the organizing committee led by Gustavo Madeira, and I wish special thanks to Gustavo Maurício for his support in the broadcast in the lectures. Thank you very much. So I gave now the word for Professor Gustavo Madeira. No, Gustavo, no, Adilson. Is Adilson here? Okay. Word.
Rapaz, eu estou live.
Thank you very much.
Yes, only to say thank you for everyone to participate in our event, and we look forward to see everyone at the fiscal. So now I pass you.
Yes, maybe Odair, Francisco.
Okay, Olympio, I want thanks Gustavo for the initiative of this meeting. The initiative, he organized everything. He invite the people. Of it is his idea. So all of us, the other organizers, have to thank Gustavo for this meeting, for the success of this meeting. Thank you, Gustavo. And also Gustavo Maurício, those Gustavos are the two Gustavos are very important for this meeting. And Gustavo Maurício solved all the problems incredibly efficiently with the small problems that we have. Is small because of Gustavo Maurício. Thank you. Thank you.
Now I give the word to Gustavo Maurício. Thank you again, Maurício. I'll give you a word for you if you want to say something. Okay? Okay. Finally, I give word to our leader, Professor Gustavo Madeira, to say something and finish this event.
I think Rodrigo has something to say. Okay, Rodrigo, please.
Okay. Hi, everyone. I would like to thank all speakers for the great lectures, and thank you very much. Thank you very much.
Adilson already speak something. Yeah. Yeah. So thank you all. As Olympio said, previous talk was the last one in our webinar. During the past 3 days, we had the opportunity of enjoying talks directly live streamed from some parts of the world like Belgium, Brazil, Italy, Spain, Sweden, United Kingdom, and United States. Top-level talks delivered by top-level speakers. For us, from the local committee, it is a great pleasure and further honor to thank each one of the speakers in the webinar. The professors, Jairo Figueiredo, who promptly accepted our invitation but could not attend the meeting for a force majeure reason. Andrei Zulkin, Augusto Ponce, Boyan Sirakov, Cláudio Anor Alves, Davi Arcoia, Denis Bonheure, Eduardo Teixeira, Giovany Figueiredo, João Marcos Duó, Lúcio Bocardo, Manuel Del Pino, and Patricia Pucci. Thank all of you which promptly accepted our invitation to take part in the webinar and shared with us, with all the participants, deep ideas and insights in a very clear and enthusiastic way. I also thank to my friends in the local committee, Professor Olímpio Miyagaki, Rodrigo Rodrigues, Adilson Pressoto, Francisco Daí, and Gustavo Mauricio, the man behind the scenes, great man behind the scenes. Thank you so much. We believe we succeeded our main motivation for this webinar. Although the pandemic is a moment to face many difficulties of all sorts, it is possible to build bridges and shorten distances. Finally, we warmly thank all the participants, each one in each live stream we had, and each one who saw or will see these videos on the YouTube channel of the graduate program in mathematics from Federal University of São Carlos. Thank you so much and keep safe. Bye. Thank you so much for attending this meeting.
Bye-bye.
Bye-bye.